Now for the second part on transformations, we're now going to focus on dilations, vertical stretches and shrinking, and horizontal dilations, which again is the result of stretching and shrinking as well. And then we're going to learn how to graph functions using a sequence of transformations. Now, in order to vertically stretch or shrink a function, just like with a vertical translation, we're going to affect the entire function itself and not the input values. So here, notice that this graph is stretched vertically. Again, we grab it from, the center from the zeros and stretch it upwards by multiplying, again, the original function with a constant, as you see this notation right there. That constant has to be a number greater than 0, however, in order for it to stretch by a multiplicity, which we call a scale factor, of its y-coordinates by c. So by multiplying again the function f of x by c, we're affecting the y-coordinates, just like when we were adding again a c to the function, we're affecting again the y-coordinates as well. Now, if I multiply by a number between 0 and 1, a positive number, in other words, less than 1, then that's going to result in shrinking the function vertically. So that's going to vertically shrink by multiplying again by its scale factor to the y-coordinates of c. So for example here, to graph the function f of x and obtain the graph of 1/2 x to the third power, well, let's see again what the coordinates are, a couple coordinates for f of x are. So let's use -2, -1, 0, 1, and 2. So if I use those input values into f, my output values are -8, -1, 0, +1, and +8. Now let's compare that with g of x. Look what happens to the y values when I input the exact same x values. Multiplying again, since x to the third power, I already know from this table here, x to the third power is going to give me these numbers again when I plug in the respective x values. All I'm doing now is multiplying x to the third power with 1/2. So since -2 to the third power is equal to -8, multiplying -8 with 1/2, that's going to equal to -4. Inputting -1 is going to give me -1/2. 0 still stays at 0, +1/2, and then +4. With the exception of 0, we can clearly see that our y values are now half of what I originally got before multiplying by 1/2. So as you can see, what's going to result in the graph is that the graph of this function, and let me do my best to draw this as accurate as possible. 3, 4, 5, 6, 7, and 8. 1, 2, 3, 4, 5, 6, 7, and 8. And at -2, -8, 1, -1, 0, 1, 1, and then 2, +8, which is going to be all over here, our graph will look like this. Again, curved. And then G, I'll do H, I'm sorry, this is H, not G. I don't know where I got G from. I'll do G in blue. G is going to put our values here. So you see again, this has been shrunk vertically again by half. And again, what's important understanding here is that our y coordinates are half of what they originally were. So let's try this one. Try to graph this function here and see what the graph is going to look like. So let's check your work. Again, let's first compare this again using input values, again using coordinates from our function. And let's see how that compares again with g. So let's plug in again -2, -1, 0, 1, and 2. So the absolute value of -2 is +2. This is +1, 0, 1, and 2. So those are the input values again for the output values for f of x. So if I input the respective numbers, this is what I get out. Now, let's compare that with g. Well, we already know again from f, taking the absolute value of these numbers is going to give me again this output. G is simply going to multiply those outputs now with 2. So 2 times 2 is 4. 2 times 1 is 2. 0 times 2 is 0. 1 times 2 is 2. And 2 times 2 again is 4. So all I did was get these numbers and now multiply them with 2. And look what happens to our graph. So we have 0, 0, 1, 1, 2, 2, 1, 1, 2, 2, 2, 2, my bad. And let's connect them. And the graph looks like that. Compare that to g. Look how now these points are stretched. At -2, the y value now is at 4. At -1, the y value is at 2. At 0, it stays the same. This point is now at 2. At 1, the y value is 2. And at 2, the y value is 4. So look how this has been stretched vertically. So this is a vertical stretch, and look what it looks like. Again, a vertical stretch, again, makes the graph narrower and looks skinnier than it originally was, while a vertical compression makes the graph wider, and it looks again like we're pulling it out. So that's the two comparisons. Now, let's move on to horizontal stretching and shrinking. Well, just like with a horizontal translation, we are affecting again the input value. So just we are still going to multiply by a constant, again by a scale factor, but that scale factor is being multiplied to the input value, and the notation for horizontal dilations is c times x, so f of c times x. Now, the difference in understanding whether we're shrinking or stretching depends on what we're multiplying by. Now, it's backwards. If I multiply by a number greater than 1, I'm actually going to shrink the graph horizontally, which kind of makes it look like I'm stretching it vertically. Notice how this point looks to be a little bit higher. But horizontally, compared horizontally, we're pulling it inward, so we're stretching it again. Shrinking it horizontally. Instead of it having the our x-intercept all the way over here, it is now sooner, and it's located down there. And the same thing on this side. Instead of having our x-intercept here, it is going inwards to this new location right there. And that's the result of multiplying our input value by a number greater than 1. And then if we do the opposite and multiply our input value less than 1, still a positive number, but less than 1, it's going to stretch the graph horizontally. So this x-intercept has been stretched outwards, and we see that we reach again the x-intercept later than sooner. And the relative maximum point again is a lot later. Instead of it being here at this value of x, it is now located at this value of x. And the same thing in the opposite direction. This intercept has now been pulled outwards, and this relative max minimum is now located there. So again, they've been pulled outwards, and as a result, this is what a stretch looks like. So for example, let's look at this graph right here. And because this is a horizontal dilation, I forgot to note this, is that it is going to divide, instead of multiplying, it divides the x coordinates by that value. So to see how does it affect the x coordinates, it's going to divide by that quantity there. And look, it'll make sense again when we look at these expressions. So let's look at this expression right here. Notice again what our coordinates are. So for f of x, let's make a table of values for f of x, which again are these points. At -4, our y value is 0. At -2, it's 4. At 0, it's 0. At 2, it's -2. And at 4, again, this coordinate is at 0. So these are the respective x's and the values of f at those x's. Let's look at what g is going to do. G of x is going to equal to f of x times f of 2 times x. So what this is going to do is that our input value is now 2 times it originally was. So what that means is that in order for us to get the exact same output values, okay, to get the exact same output values, our x values have to be half of whatever this value is. Because in order for it to get 0, we need again 2x to be half of what it originally was, because this number needs to be multiplied with 2, but we still want the number again to be 0. Well, we already know from the previous table the way to get 0 is if x is equal to -4. Well, in order for this right here to equal to -4, in order for 2x to equal to -4, x has to equal to -2. I'm dividing this value by this number right here. So this has to be -2. Now, in order for our output value to be 4, we need the x to be -2. So what does that mean about f of x? Well, f of 2x f of 2x, which is again our 2x, in order to get this output to be 4, we need this again to be the number -2. Well, we need this to give us an output of -2. So that means that 2x has to equal to -2. And well, that means that x equals to -1. So what I'm doing again is dividing this by 2. So I'm dividing this number by 2. So that's -1. I'm sorry, I forgot to write this as -2. And that's what I'm going to do with the rest of these values here. I'm going to divide all of these numbers here by 2. So 0 divided by 2, 2 divided by 2, and 4 divided by 2 is going to give me those values there. And look at how when I plot these points, you're going to see that the graph has been shrunk horizontally. So this point to this point, this is now going to be -2, 0. -1, 4 is where that relative max is located at. We're still going through the origin, that doesn't change. This v, the change in direction here in the v, is at 1, -2, and now we're at 2, 0. So our graph looks like this. And look, see how we compress this horizontally. We pushed again, this got pushed inward along with this, and this one as well. They all got pushed inwards by a factor of 1/2. So we divide by this number because we're essentially again solving this equation here in order to maintain the exact same output values. So let's compare this again to H. So for H, you know what, let me do this in blue. Let me go back and put them in blue instead, so I can use red for the stretch. So for the stretch, by multiplying our x by 1/2, what we're trying to do is figure out, okay, what does x have to equal to now in order for our output values again to stay the same. So again, the 1/2 on the outside simply multiplies our current output values by 1/2. But now since the 1/2 is being multiplied with the x, what this is stating and suggesting is, okay, all right, we're trying to figure out what does x have to equal to now maintain the same output values. Well, we know from, again, the original parent function, in order to get the output value of 0, our x value had to be -4. So now multiplying x with 1/2 means we need to get 1/2 x to equal to -4. Well, solving this equation multiplies both sides by 2, and we end up multiplying -4 by 2. Again, dividing -4 by 1/2, in other words. So we end up with -8. And if I do that with this, with again with -2, and I multiply -2, if I divide -2 by 1/2, I end up with -4. Dividing 0 by 1/2, that's still going to equal to 0. Dividing 2 by 1/2, that's equal to +4. And dividing 4 by 1/2 is equal to 8. And now this works out because -8 times, substituting in -8 here for x, -8 times 1/2 is equal to -4. And well, -4 gives me an output of 0. -4 times 1/2, that's equal to -2. And -2 gives me an output of 4. 0 times 1/2 is equal to 0. And 0 gave me an output of 0. So that's the same now. And the same thing with these two things. 4 times 1/2 is 2. And since 2 equals -4 in the original parent function, in this transformation, we have the same output value. And since 8 times 1/2 is 4, our output value again is going to equal to 0, and we end up again with 0. Excuse my notification, sorry about that. So look at how that's going to look when we stretch this out. We have a point at -8, 0, which is somewhere out here. Our -4, +4, our 0, 0, our 4, -2, and our 8, 0, which again is going to be out on the outside. Look how this has been stretched horizontally. Let's now check this one. All right, so pause the video and see if you can figure out what the graph of this parent function, this f of x, is going to look like when we perform these two transformations. So let's check our work. So for the current function, f of x, our input and output values from left to right are the following. Now, what is g going to do? G of x which equals f of 2 of x, means that in order to get the same output values, we have to divide all of these input values by 2. So if I divide all of these numbers by 2, when using these numbers, look what our output value is going to be. They're going to be the same. Look, -1 times 2 is -2. And since this is the original function, we know that in the original function, -2 gives me an output of 0. So this is also going to give me an output of 0. When I plug in 0 times 2, that's 0. And I know again from the original function, an input value of 0 gives me an output of 3. So this is also going to give me 3. And then the same thing is going to be true with all the other ones. I'm going to get the exact same output values. So our graph looks like it's been horizontally again compressed. -1 0, 0 3, 1 0, 2 -3, and 3 0. And for h, which is equal to f of 1/2 x, that's going to multiply all of the x values by 2. Well, divide by 1/2. It's going to divide all of the x values by 1/2, which is the equivalency of multiplying by 2. Dividing by 1/2 is the same thing as multiplying by 2. So we end up with -4, 0, 4, 8, and 12. So our graph would again have the same output values. And just to re-emphasize why this works, because now if I plug in 4 into again this function where my input is now half what it originally was, 4 times, let me write this down, f of 1/2 times 4, that's going to equal to f of 2. And I know from the original function, the value of f of 2 is 0, because when x is equal to 2, the y value is 0. So this is going to equal to 0. This equals to 0. And you see, it matches again exactly there. And if I do the same thing with 8, I'll see that the y value is going to be -3. And then again, the same thing with 12. 12 times half is equal to 6. So f of 6, again, is equal to 0. So all I'm doing is just simply, again, dividing all of these original x coordinates by 1/2 to figure out what the new x coordinates have to be to maintain the same y coordinates. And now, how does that affect it graphically? Well, the way it affects it graphically is by stretching this by 2 horizontally. So it stretches it horizontally. So at -4, we have a point at 0. At 0, we have a point at 3. At 4, we have a point at 0. At 8, we have our point at -3. And then we have a point all the way over here at 12, somewhere way outside the graph. And look, it's been stretched horizontally. Now, to perform a sequence of transformations, again, just to review again what the transformations are, to shift something vertically, we add a constant, then that's going to raise the graph c units up. If we subtract it from our function again, that's going to lower it c number of units. To shift it horizontally, we add or subtract again to the input value, not to the function itself, but to the input value, and adding shifts it to the left, while subtracting will shift it to the right. To reflect it across the x-axis, which is a vertical reflection, we simply multiply the parent function with a negative. And to reflect it across the y-axis, a horizontal one, we multiply the input value by a negative. And then just like I discussed, the last one, to cause a vertical shift, we multiply our function with c, and that's going to affect, again, a vertically affecting the y coordinates of the function by multiplying those numbers by c. And the same thing again with multiplying by a positive number less than 0. That's going to affect the y coordinates. Each y coordinate gets multiplied by that constant, and it's going to shrink them because we're multiplying by a number that is less than 1. And then the opposite occurs again with horizontal stretching or shrinking. F of x times c is going to divide each x coordinates by that c, causing a horizontal shrink if that number is greater than 1, and it's going to result in a horizontal stretch if that number we're multiplying is less than 1, a positive number, of course, less than 1. And that again is going to divide each x coordinate of our function by that constant. Now, if we have again all of these transformations, the sequence to transforming a function is by first identifying any horizontal shift, then going to any stretching or shrinking vertically or horizontally, moving on to identifying any reflections over the x or y axis, and then finally looking at the vertical shift. So this is again the sequence and the order of transformations where we have multiple ones, and we need to look what the graph will look performing these multiple transformations. So for example, here we have this function f of x, and we want to transform it by performing these operations again to this function. Well, we start off by first looking at the horizontal transformation. So that's the input value of x minus 1. So x minus 1, remember, is going to shift this 1 unit to the right. Well, how is that going to affect the coordinates? That's going to move this coordinate of negative 4, 0. Let me actually write all of these coordinates first. Negative 4, 0, negative 2, 4, 0, 0, 2, negative 2, and 4, 0. That's going to shift this point 1 unit to the right. So this coordinate is 1 unit to the right is at negative 3, 0. This coordinate 1 unit to the right is negative 1, 4. Negative 3, 0. I'm sorry. I meant to say negative 3, 0 for the first one. Negative 1, 4. 0, 0 shifted 1 unit to the right is at 1, 0. 2, negative 2 is going to be at 1, negative 2. I'm sorry, 3, negative 2. And 4, 0, 1 unit to the right would be now at 5, 0. So notice that what happened here by shifting again and putting x minus 1, which means shifting it 1 unit to the right, all of my x values have been increased by 1 value. All my y values are the same, but all of these are now 1 unit higher. So I added 1 to every single one of these to get these new values there. Now we look for any shrinks. Well, here we are multiplying by 1/2. And because it's on the outside, that's a vertical dilation, which is going to affect the vertical coordinates, which are the y coordinates. So the 1/2 is going to multiply all of these y coordinates by half. And this is where the locations would be again after shifting it 1 unit to the right and shrinking vertically by half. Now we look for any reflections. Well, we also have a vertical reflection. The negative sign again on the outside is a result of a vertical reflection. And again, a vertical reflection affects the vertical coordinates, which are the y coordinates as well. So they're going to be flipped upside down, making every positive into a negative and negative into a positive. It just switches. So that's going to be 0. Sorry, wrong one. The 2 becomes a negative 2. 0 still going to be 0. 3 and positive 1 now. And 5 will flip upside down. It's still going to be at 0 because it's at the center. So we flip this upside down. And then finally, the last thing that we have, and then we'll graph it, is the vertical translation. So the vertical translation is going to increase this 3 units up. And again, because it's a vertical translation, it's going to again affect the vertical coordinates, which are the y coordinates. So the final x and y coordinates will be -3, 3, -1, +1. 1, 0, 3 units higher is at 1, 3. 3, 1, 3 units higher is at 3, 4. And 5, 0, 3 units higher is at 5, 3. So let's plot these points here. -1, 1. 1, 3. 3, 4. And then 5, 3. So we're going to have our u, our, again, quadratic piece of the graph, and then our absolute piece of the graph, or v looking portion of the graph. So this is our transformation. So as you notice, again, performing a horizontal transformation affects the horizontal coordinates, which are your x coordinates, and performing a vertical transformation affects your vertical coordinates, which are your y coordinates. So let's do another example. Let's see, pause the video and try to graph this function here. So let's check your work. So for this function, the x and y coordinates for f, as indicated on our graph, are -2, 0 from left to right, 0, 3, 2, 0, 4, -3, and then 6, 0. So again, -2, 0, 0, 3, 2, 0, 4, -3, and then 6, 0. Well, to perform again this transformation, let's take it one step at a time. We'll start again first with any horizontal translations. So our horizontal translation is adding 1, which is going to result in shifting this graph 1 unit to the left. So that's going to move every single one of these things 1 unit to the left. And the location of those coordinates is going to decrease the the x values by 1. So -2, 0 is now at -3, 0. Our next point is now going to be at -1, 3, 1, 0, 3, -3, and 5, 0. So all I did was just simply subtract 1, and that's how I shift to the left by 1 unit to my x coordinates. Now, looking for stretches, so in this case a shrink, the 1/3 is going to multiply. Since it's a vertical dilation, it's going to affect the vertical coordinates and multiply all of these vertical coordinates by 1/3. Multiplying 0 by 1/3 is the same. Multiplying 3 by 1/3 is 1. 0 times 1/3 is 0. -3 times 1/3 is -1. And 0 times 1/3 is 0. The next transformation that we look at is to now look at the reflection before our translation. So our reflection is it's a vertical reflection, so that's going to affect again the vertical coordinates, which are the y coordinates, and we're going to end up with the opposite y coordinates. Well, 0 doesn't have an opposite. The opposite of -1, of +1 is -1 again. The third term, 0 doesn't have an opposite. Negative 1 has an opposite of positive 1, and again, 0 does not have an opposite. And then finally, the last transformation is going to be the -2, which again is a vertical translation. It's going to slide it vertically 2 units downwards. So that's going to affect again the vertical coordinates, which are your y coordinates, and it's going to decrease those coordinates by 2. So subtracting all of the y coordinates by 2, we end up with -2, -3, -2 again, -1, and -2 again. So let's plot these points from here. So -3, -2, -1, -3, positive. I just saw an error right here. I don't know why I put this as a -1. This should be a +1. So at +1, here, this point there, this point right there, that should be +1 too. So at +1, the y value is -2. Then we have our next point at 3, -1. And then our last point is at 5, -2. So look at what our graph looks like now. So our graph should look like this. So notice that the horizontal, we didn't stretch it horizontally, and notice that that didn't change. Notice that the distance from -2 from this endpoint to this endpoint here, let me use the blue to send out, from this endpoint to this endpoint right there is still the same. It's a total of 8 units. And because there was no horizontal dilation, that is still the same. From -3 to 5, that is still going to be 8 units. What this change is, again, the height of these V's. Normally, this height, again, was 3 units, but now the height of this V is 1 because of that vertical shrink. And the same thing with this V. This V had a height of 3 units, and now, again, it's only 1 because we're taking a third of that original vertical height. And this is what the graph will look like. Notice that it's also upside down. This V is now this V right there, and the V that was underneath the x-axis is now upside down. And of course, the translations of shifting its 1 unit to the left and 2 units down moved it again slightly, so it's not lined up above each other or below each other, and again, and well, directly above and directly below because of the 1 unit to the left and the 2 units down. All right. So that concludes again our notes on this section. If you have any questions, please send me a message on either Remind or through email. And again, I appreciate you watching, and I hope you have a great day.